Okay, so let's go to our geometric distribution now. So the setting here is that we keep on repeating an experiment until you have success. So until the first success. And anytime I use the phrase experiment here, it means independent. Anytime we use the phrase experiment in this class, it will be independent. So I won't usually even bother to say it. But I'm mentioning it here because if you go and look at the examples in the book, they'll make a point of saying they're independent. So I keep on doing the same procedure over and over again until I succeed. So if at first you don't succeed, try again. And the question that we'll be looking at is how long does it take? So let x be the number of attempts until success. And this will be a random variable because I might succeed the first time, or it might take me 10 tries. And we want to find the PDF of it. So let's look at a couple of examples, or a couple of cases. Let me just note down here, P will be used to denote the probability of success each try. Okay, so what's the smallest value we could have? I keep on repeating an experiment until I succeed.
1.
Yeah, exactly. So if I tried 0, that can't happen. If I never try something, I can't succeed at it. If I succeed the first time, well, that's P. Right? P was defined as the probability of success in one trial. So it basically goes straight back there. Now let's look at 2. So if my first success is attempt 2, then what does that tell us about attempt 1?
It didn't go so great.
Yeah. So that means fail and then succeed. So what's the probability of failure on my first attempt?
0.
1. Oh,
I heard a couple answers. So what was the probability of failing my first attempt?
The probability of failing px1 is 0.
Well, the probability of succeeding is P. So failing is 1 minus P.
1 minus, yeah.
Yeah. The first formula on the screen here was a 0, but that's not actually what we're looking at. We're saying something else. So fail is 1 minus P. And then means we multiply. And what's the probability I succeed after that? Well, I give it a try, and the probability of succeeding is P. So the probability that it takes 2 steps to succeed is, whoa, what did I just do? Is 1 minus P times P. And this was the reasoning. Let's go one more step and then see if we can come up with a formula for the general case. So for 3 steps, what happens in the first step? So I want to succeed on attempt number 3.
So you got to fail twice.
Yeah, so fail, and then fail, and then succeed. So the chance of failure on attempt 1 was what?
1 minus p.
And then we have and then we do that again, and p. So you can probably see a pattern here. We keep on failing until finally we succeed. So the general formula will be 1 minus p a bunch of times until you finally succeed. And this would be true if k is a positive integer. If I put k equals 0 in here, this is going to give me something else that's not correct. But that's okay because this only says k is a positive integer. And as we've learned before, any condition that is not described in your PDF is automatically 0. So it agrees with this case by default because this was not included in my answer and therefore it's a 0. So let's look at an example. Let's suppose that 2 teams are playing. A series. And my favorite team historically wins 40% of games, so they're at a disadvantage. Historically, just to emphasize, it does not apply to this series, has won 40% of games. What is the probability I'll say their first win is game 1. And then their first win is, let's say, game 3. And then we can ask, they win one of the first 3. Okay, so maybe somebody can answer the first part. What is the chance they win game 1?
40.
Yeah, we don't even need to use geometric, but we could. So if you used geometric, then that would be this statement. The probability your first win is in game 1 is P. But really, if I have a 40% chance of winning each game, that's the chance I win game 1. Game question mark. That wasn't my plan there. Their first win is game 3. So when we're looking at something that's not immediate, you need to justify your choice of a distribution. So I could write down the formula from this question, but then it needs to be explained why that's correct. So according to the data here, they win 40% of games. And we're looking for the first success.
Can you scroll down a little bit?
Does that mean you don't see what I'm writing?
I can't see anything below 2. Yeah, there.
Okay, and then their first success is game 3. And so that means it should be geometric. When we look at first successes, we want geometrics. So this is a justification for using geometric. Now there's one thing I left out of this question, which is actually significant. If you think about how games actually work out, there's traditionally a home team advantage, and they sometimes use the phrase momentum to refer to the fact that if a team has won a game, it seems to increase their chance of winning the next one. So these outcomes are probably not quite independent, but for our purposes, we'll consider it that way. And typically a question would say something like assume independence. So there are, famous counterexamples like where the Red Sox came from behind to win the World Series, even though they had lost a bunch of games at the start. But there are various factors that tend to make these not independent. And so the geometric answer for first is game 3 would be px of 3. P was 0.40. And this is 0.144. Can anyone suggest a way to answer this last question? What is the probability they win one of the first 3 games? And in case it's unclear, this does allow them to win more than one. It's just saying at least one.
Would you do a summation?
Yeah, so we could add up the 3 answers. We haven't done px of 2, but we've done 1 and 3, so it's easy enough to fill in the missing value. So this is 0.40. This would be they lose and then they win. And then this one we just found. 0.4 plus the next term plus 0.144, and that's 78.4. Now this is a reasonably large number, but that shouldn't be surprising. If my team almost has a 50% chance of winning each game, we expect they're going to win 1 or 2 out of the first 3. So we should have a decent chance that they've won at least 1 game out of the first 3. Now there's another formula that can be used. And this would be to observe that the only way this could go wrong is if they keep on losing. So I could say the chance it takes more than 3 games is 1 minus the chance they keep losing. Or that is the chance they keep losing, sorry. This would be lose, lose, lose. In this particular case, I would get 0.216. And so the probability that they didn't keep losing is 1 minus that. So either approach is fine. You can either, well, when we have small numbers, either approach is fine. If I was looking at something much further out, like 10 games, then adding up 10 cases is harder than just taking this one term. Now, when we've been talking about distributions in the past, we didn't just stop when we knew the PDF. We then went on to talk about things like expectation and variance. So for our geometric distribution, we have E of x, and that would be adding up every possible case. So add all possibilities of k times the probability of k. And it's possible to evaluate this sum. It's actually the derivative of a series that is not too hard. But we also can figure this out intuitively. So let's take a different example. Let's say I have a 6-sided die, and I want to roll a 6. Well, there's about a 1 in 6 chance that I roll it on my first term. And if I keep on trying, I might ask, well, how long is it going to take until that first 6? And if there's a 1/6 chance of success each time, turns out the answer is 1 over p. So you can calculate this sum, or you might be able to convince yourself with some intuitive argument like that. And if you want a proof of that, the book does not give one. I can give it to you outside of class time if somebody wants to see the proof. And then for variance, 1 minus p over p squared. And we can use a similar type of summation. So we would find the sum of the squares and then the difference. And this can be found with some derivatives. Now that square looks like it might not be a square. So let me make it clear what that is. So that 2 goes right above the p. So looking down to my teams playing their game thing, I could ask, on average, how long does it take until my team wins? So how does that question relate to the various quantities that we've looked at here? Anybody? Okay, well, average is expectation. This is asking what is the expected number of games until they win.
Two and a half.
Yeah, so we take 1 over p, which is 1 over 0.40. And as was just stated, that will be 2.5. And this answer makes sense. If they only play 2 games and they usually win 40%, then they probably didn't win a game. I mean, maybe they did, maybe they didn't, but 40% of 2 is less than 1. If they played 3 games, 40% of 3 is more than 1. So somewhere between game 2 to game 3, they should win their first. Now, obviously, games don't come in half round increments. This is just saying sometimes they might win the first game. Sometimes they'll win the second. Sometimes it'll be the third. And when we average over all those numbers, it comes out to 2.5. This doesn't even mean half of the time is 2 and half the time is 3. There will be bad times where they play 5 games and still haven't won. But on average, 2.5. And the last part we look at is chapter 4.5. I should have numbered this. This was 4.4. And I'll clear the screen in a minute, but I'm just going to point out what changes here. So in this question, we looked at first success. There are lots of situations where first isn't what we want. So for example, if you're playing baseball, the third strike is the one that makes you out, or the fourth ball is the one that you walk on. So in that case, if I want to get walked, it might be how long does it take until the fourth ball? A more complicated question would be, does that happen before 3 strikes or not? And that's not something that we're ready to answer for now. But we could answer a question of, if I know the percentage of balls that are thrown, how many pitches should it take before 4 balls have been thrown? And hopefully they're all the same batter, but they might not be. So that will be negative binomial. So again, to contrast with the previous case, we have repeated experiments again, but we want to continue until k successes. Now, we're not going to use the letter k because k has been used as the counter in the PDF, so I'll use r instead. And the PDF for x, I'll write the formula down and then explain it. It's a little bit strange. So if I want to have r successes, and those r successes should happen in k attempts, then I know the last one was a success. Because if I had done all of those successes before the end, then the number of experiments it takes would be less than k. What do I know about the time before that?
They were all failures. So they're all 1 minus whatever the chance of success was.
Yeah, so in the geometric case, we wanted the first success to be at that last time. But now we want r successes. So how many successes happened before the end?
That would be k minus 1.
Yeah, almost. R minus 1.
Oh,
So we have r minus 1 successes, and then we have our rth success, and that's when we stop. Because in this setting, it was the number of experiments until the rth success. Okay, well, we've actually looked at something like this first bit. So if I have k minus 1 attempts, what is the probability that I have this many successes? Well, that's a binomial probability. You do a bunch of attempts, you get a certain number of successes. And the binomial probability formula is take the number of attempts and choose the number of successes. Then I have my final term here. So this last success will go at the end. So that big first expression was the probability that I have r minus 1 successes in the initial sequence. And then I succeed on the last try. Well, there's no reason to write these separate. I have a p here and some p's here, so I might as well combine them. And looking at this exponent, the negative ones cancel out. So I can simplify this somewhat. I'll have k minus 1, choose r minus 1, p to the r, 1 minus p to the k minus r. So that will be the probability that the kth success occurs. The r success, sorry, occurs on the kth attempt. Kind of messy. So in the question we looked at before, my favorite team has a 40% chance of winning a game. And I talked about them having a series. Well, usually a series has a fixed number of games, like 3, 5 games, 7 games, whatever. So let's do a 5-game series. And I'm going to ask 3 different questions here. First, what is the chance my favorite team wins the series in 3 games? And for the few people who know less about sports than I do, which is not much, in order to win a 5-game series, you need to win 3 games or more. So win 3 or more games to be the champ. Now, as I promised, I don't know much about sports, so I don't even know if a team wins the first 3 games, do they always end the series, or do they only do that in playoffs? I'm curious. Anybody have an answer? If 2 teams are scheduled to play the 5 games, do they actually always play them, or do they quit when one of them's won enough games?
And the playoffs to quit.
What about in regular
think-
season? Okay, yeah, someone else says they stop. So maybe they always stop after 3. But it wouldn't actually change the outcome of the series if you played all 5 games. If one team wins the first 3, then no matter what happens afterwards, they still win the series. So anyway, so let's say, what's the chance my team wins the series in 3 games? Well, looking at the language here, I want to have 3 successes. P is the probability of success each time, which is 40%. And K, the number of games we're going to play, is 3. I think things have been getting cut off for some people, so hopefully that isn't good enough there. And so the question is asking, for the probability that x is 3. Because k is 3. So the formula was k minus 1, so 3 minus 1. Choose r minus 1 times p to the r, 1 minus p to the 3 minus 3. And we're going to need to calculate a few of these numbers. So rather than plugging these in one at a time, let me write all the cases down. Oops, that's going to be later questions anyway. So we will write that one down, and then in a minute we'll come back and do the general one. So this will be 6.4%. So that's a pretty long shot, and that's not surprising given that my favorite team doesn't even have the advantage in the series. Then let's say, well, what's the chance they win in 4 games? That means that they do not win the series in 3 games. They have to play to that last game. So this is also a negative binomial case because we play until that specific point that has been given. So we still have 3 successes. We still have 40% chance each time. And now we win in k equals 4. So the formula has k minus 1. So that will be 4 minus 1. Choose 3 minus 1. Then p to the r. 1 minus p to the 4 minus 3. And that will be 11.5%. And then, well, to win the series, you could take 5 games. So we still have a negative binomial case because we are playing the series until the 3rd success. But now we win in k equals 5. So 5 minus 1, choose 3 minus 1. And then I have to plug all of that in. And this will be 13.8%. And the question that we really want to know is, what is the chance they win the series? So how can I answer this question? Anyone?
A summation.
Yeah, so winning the series just means that they won in 3, 4, or 5 games. Notice that you actually can calculate this for 6, 7, 8, and so on. What that would mean, let's say we took px of 8, it would mean that he had to play 8 games before they would finally win a 3rd. So you don't have an 8-game series, but you can still calculate what is the chance it would have taken that long? Okay, so we'll add up these three numbers, 0.064, 0.115, and 0.138, and get 31.7%. So if you went into a series and your team was at a disadvantage, but a slight disadvantage, there is still a chance they'll come out ahead. And that's what makes, playoffs exciting. Even when you go into the finals and, let's say we know that the Celtics is the better team, then the fans of the Warriors still want to watch because there's a chance that their team will come out ahead. And here it's saying if their team were to win 40% of matchups typically, they still have almost a 1/3 chance of winning the series. Now let me make one final observation from this before we call it quits. So normally we don't think of one game as a series, but let's just pretend that it was. If I said we play a 1-game series, then what is the chance my team wins that 1-game series? I suppose the arrow probably shows you 40%. So in a 1-game series, my team has a 40% chance of being the champs. In a 3-game series, it has dropped. A 5-game. If I had a 7-game series, it would drop even further. And this makes sense because the more games you play, the more accurately you'll be able to understand which team is better than the other. So if my team is worse, then I would prefer that they play only a small number of games because there's the highest chance that the outcome doesn't match the better team winning. If my team is better, then I would prefer a really long series. So, if you went into, let's say, the Baseball World Series, I believe it's 7 games. And so if my team is the better one, I like those 7-game series because it makes it more likely that my team will come ahead. If my team is not as good, then I would rather have a really short thing like the Super Bowl where you only have 1 game. So in the Super Bowl, you have a much higher chance of the wrong team coming out as the champs than you do in the World Series where you have 7 games. And we can calculate, as we saw here, what those probabilities are, although this is under ideal circumstances. So like I mentioned, we're ignoring home team advantage, we're ignoring the idea of momentum, but in some sense, we're able to come to conclusions. You can also find expectation and variance in the book if you need those, but I'll skip that for now. Next